Plastic and polymers. What is the meaning of plastic? Are all plastic polymers? Or are all polymers plastic? The word plastic comes from a Greek word plastikos, meaning to mold. Generally, plastics refer to synthetic polymers. Plastic are polymers, but not all polymers are plastic. Plastic are classified into two types: the thermosoftening polymer and the thermosetting polymer. Thermosoftening polymers, aka the thermoset, consist of a tangled web polymer chains and are attracted to intermolecular forces. Because of the weak intermolecular force, the object when heated turns into liquid. Then, if you freeze it or just put it in a cold place or cold water, it hardens. An example of thermosoftening polymers are glue stick or wax. When exposed to heat, it'll turn into liquid, but when exposed to cold, it hardens. You can also reshape it or remold it.
Thermosetting polymers, di ba kanina sa thermosoftening nagkakaroon ng attraction yung mga polymer chains pero kapag nainitan, naglalayo na sila or humihina yung attraction. Pero sa thermosetting polymers, kapag meron kang polymer, ang nangyayari kapag ininit mo siya, nagkakaroon sila ng connections, lalo sila nagkakapit-kapit sa isa't isa. Yun ang tinatawag nating cross-links between molecules, kaya kapag ininit mo to, tapos nag-set na siya, di mo na siya pwedeng ulitin, magde-deform. Hindi na siya pwedeng ma-recycle. Di katulad ng glue stick na pwede mong tanawin at ulit-ulitin. Thermoset na to, once na init mo siya, wala na, matigas na. Pero yung kagandahan nito, yung plastics is matibay. Yung example naman nito yung gulong kasi, need ng mga gulong matibay. Kasi if mainitan yung gulong, tas mainit din yung kalsada, matibay siya. Hindi siya malulusaw. Polymer can be arranged in a number of ways. The arrangement of the polymer chains affects their properties such as whether they are stiff or rigid, crystalline, or amorphous for asymmetric monomers. So may for basic polymer structures tayo dito, merong linear polymers, branch polymers, cross-linked polymers, and network polymers.
Linear polymers resemble spaghetti with long chains. The long chains are typically held together by weaker van der Waals or hydrogen bonding. Since these bonding types are relatively easy to break with heat, linear polymers are typically thermoplastic. Heat breaks the bond between the long chains, allowing the chains to flow past each other, allowing the materials to be remolded upon cooling. The bonds between the long chains are reformed. Polymer hardens. Some examples of polymers include polyethylene, a thermoplastic used in many consumer products such as bags, bottles, toys, etc. Polypropylene, a thermoplastic widely used in packaging, household goods, etc. And the last one is polyethylene terephthalate, a thermoplastic widely used in beverage bottles, clothing, and etc. Branch polymer resembles linear polymer with addition of shorter chains hanging from the spaghetti backbone. Since these shorter chains can interfere with efficient packing of the polymer, branch polymers tend to be less dense than similar linear polymers. Since the short chains do not bridge from longer backbone to another, heat will typically break the bond between the branch polymer chains and allow the polymer to be thermoplastic. Although there are some very complex branch polymers that resist this melting and thus break up, becoming hard in process before softening. They are thermosetting. Here are some examples of branch polymers. Polybutadiene, a synthetic rubber used in tires, cables, etc. For number 2 is polysibutylene, a synthetic rubber with excellent toughness and flexibility. For number 3 is polypropylene glycidyl ether, a flexible adhesive polymer used in a variety of applications, including paints, adhesives, and plastics. Polyethylene covinyl acetate, a thermoplastic with excellent flexibility and impact resistance, used in packaging, toys, etc. Here are some of the examples of branch polymers. High-density polyethylene, or HDPE. As you can see, smaller lang yung mga branches niya, kaya mas madali siyang masiksik, so denser to. While in linear low density polyethylene or LLDPE have a much longer chains, pero regular yung interval niya, so pwede pa rin siyang siksikin. While in low density polyethylene or LDPE, larger yung chains niya, so mahirap siyang siksikin, so it's less denser. So pwede siyang lumutang sa tubig katulad ng linear low density polyethylene.
Cross-linked polymers. Cross-linked polymers resembles a ladder. The chain link from one backbone to another. So unlike linear polymer, which are held by weaker van der Waals force, cross-linked polymers are tied together by a covalent bonding. These much stronger bonds makes most cross-linked polymers thermosetting, with only a few exceptions to the rule. Cross-linked polymers that happen to break their cross-link at relatively low temperature. Example of these cross-linked polymers are polyurethane, a thermoset plastic with excellent flexibility, impact-resistant, and durability, used in numerous applications, including furniture, footwear, and cushioning. Polystyrene, a thermoset plastic with excellent stiffness, impact-resistant, and chemical-resistant, used in numerous applications, including packaging, electronic parts, and appliances. Third is explosive resin, a thermoset plastic with excellent strength, impact resistant, and corrosion resistant, used in applications such as structural adhesive coatings and composite material. Silicone rubber, a thermoset polymer with excellent corrosion resistant, electrical insulation, and thermal stability, used in numerous applications such as insulation, gasket, and sealing. Next is network polymers. Network polymers are complex polymers that are heavily linked to form a complex network of three-dimensional linkage. These polymers are nearly impossible to soften when heating without degrading the underlying polymer structure and are those thermosetting polymers. Example of network polymers are exposed resin products, silicone elastomers, polyurethane foams. Now let's proceed to copolymers. If a chemist is synthesizing a polymer utilizing two distinct starting monomers, there are several possible structures as shown in the figure below. The four basic structures as the four basic structures are random, alternating, block, and graph. If the two monomers are randomly ordered, then the copolymer is not surprisingly referred to as a random copolymer. In an alternating copolymer, each monomer is alternated with the other to form an AB-AB-AB-AB pattern. In black copolymer, more complex repeating structures are possible. For example, AAA, BBB, AAA, BBB. Graph polymers are created by attaching chains of a second type of monomer on the backbone chain of a first monomer type. These are the figures of four structures of copolymer: random, alternating, block, and graph. Now let's proceed to properties of polymers.
Properties of polymers. Heat capacity, the extent to which a plastic or polymer acts as an effective insulator against the flow of heat. Thermal expansion, the extent to which the polymer expands or contracts when heated or cooled. Crystallinity, the extent to which the polymer chains are arranged in a regular structure instead of a random fashion. Permeability, the tendency of a polymer to pass extraneous materials. Elastic modulus is a quantity that measures an object or substance's resistance to being deformed elastically For example, non-permanently when stress is applied to it.
Tensile strength. The strength of the plastic, the force that must be applied in one direction to stretch the plastic until it breaks. Tensile strength refers to the strength of plastic material is measured by the force required to stretch it until it breaks. This property is important when choosing a plastic for application that involve pulling or stretching force as it ensures durability and safety. Resilient. The ability of the plastic to resist abrasion and wear. Resilient in the context of plastic refers to its ability to withstand abrasion and wear without significant damage. Resilient is an important factor to consider when choosing plastic for application that involve frequent contact or rubbing against other surfaces. By selecting plastic with good resilience, you can ensure durability and resistance to wear and tear. Refractive index. The extent to which the plastic affects light as it passes through the polymer. The refractive index of plastic material measures how much it affects the path of light as it passes through the material. It also impacts the appearance of a plastic material, including its transparency and the way, the way it reflects. Reactivity. Most polymers are not affected by air or water, and many are not affected by chemicals that make plastic durable and safely contain and protect many substances. Most polymers or plastic are unreactive to air, water, and many chemicals. This means they are they are not easily affected or degraded when exposed to these elements. Their molecular structure and strong chemical bonds contribute to their stability and resistance. However, it's important to consider specific properties and compatibility with the intended environment or substance. Resistant to electric current isolation. Most polymers do not conduct electricity. Most polymers are insulators and do not conduct electricity due to their molecular structure. This property makes them suitable for electrical insulation applications. However, there are also conductive polymers that have been engineered to exhibit electrical conductivity.